Hi, welcome to my presentation. I'm Kristine Haley. I work in the Island Nanoscale Lab in the Department of Physics and Astronomy. My research is on strain mapping of small angle twisted bilayer graphene. My research focuses on the fabrication of crystal heterostructures to analyze and improve current techniques that will minimize strain and allow the study of the superconducting state. So what does all of this actually mean? Basically, I create artificial crystals using boron nitride and graphene. So this is a schematic of what a typical crystal will look like. There is a top and bottom layer of boron nitride, which serves as a structural support of the twisted bilayer graphene that's sandwiched in the middle. Now, twisted bilayer graphene is a mouthful, but it's really quite simple. You may be more familiar with graphene's bulk parent, graphite. Graphene is a one atom thick lattice of carbon with a hexagonal structure and is 200 times stronger than steel. So stacking two of these single layers of graphene on top of one another with one that's been rotated at an angle, and we get twisted bilayer graphene. Now we use graphene twisted at a specific angle of 1.1 degrees because a recent discovery has shown that it becomes a superconductor at low temperatures. And a superconductor can carry electric current indefinitely without energy loss. So this is really cool because devices that use electricity, such as your laptop and cell phone, would all be much more efficient and consume less power. However, during the creation of these crystal heterostructures, strain occurs. And small variations in the crystal structure from strain are predicted to destroy the superconducting state. So my goal is to analyze and improve current techniques to minimize that strain in order to study the interesting and neat phenomena that occurs. I'm going to briefly walk you through a crystal that I created and the analysis on strain variations. And to do this, I will explain crystal fabrication, Raman spectroscopy and Raman modes, mapping, and strain analysis. Creating a crystal is a multi-step process consisting of exfoliation and screening, material manipulation, layer by layer assembly, and a plethora of patience. So to begin, I take bulk material and I exfoliate it into two-dimensional flakes onto a silicone substrate. After exfoliation, I basically go on a search to find the flakes that are best suited for my needs. So these three flakes are images I took using an optical microscope to create the crystal. So I have my top and bottom layers of boron nitride, which again serves as a structural support, and then the monolayer graphene will become twisted bilayer graphene in the assembly process. And one thing to keep in mind is just how minuscule these flakes are. They are invisible to the naked eye and are about the same size and diameter to a white blood cell. Due to the size and fragility of these flakes, assembling them into a crystal structure is an intricate process. I pick up the flakes individually and stack them on top of one another. I do this by using a few tools: a microscope, a micromanipulator, and a glass slide that attaches to the micromanipulator. The stage of the microscope holds the substrate with the flake of interest. The micromanipulator is a tool that allows me to adjust the position of the slide with very high precision. And the final component is the glass slide itself. I start with a plain glass slide and I create a bubble on one end. So here is an up close of what that bubble looks like. It is created using a rubber material called PDMS, which you can see in the very center. On top of that bubble, which I have outlined in yellow because you can't see it, is a thin film of PPC. And PPC, when heated to very high temperatures, it imitates a lamination type of process that assists in picking up the flakes. And basically, the glass slide serves as a building playground for the flakes to be stacked on top of one another. To assemble these flakes into a crystal, I use a combination of techniques. I use heat application, rotational twisting, and mechanical squeezing if air or debris gets trapped between layers. The first step is to pick up a boron nitride flake. From the schematic, you can see that the boron nitride flake is on a substrate that sits to the stage of the microscope. Using the micromanipulator, I adjust the position of the glass slide to go down to the stage and pick up the flake. Here is an optical image of what that looks like. Next, we need to pick up the monolayer graphene, and the process is quite similar. We go down with the glass slide, but here I only pick up half of the graphene. I then twist the stage at a 1.1 degree angle, and then I go back down to pick up the other half of the graphene. Here is a high contrast image of what that process looks like. In the bottom right corner, you can kind of make out where that twisted bilayer graphene, and those little red dots indicate there were some bubbles of debris or possibly air that got trapped in between. Next, we need to encapsulate the graphene with another boron nitride. So this is basically the same step as step 1. We just go down, pick up the boron nitride, and come back up. And here is the optical image of what that looks like. So the bright yellow was step 1. And then step 3 is this little triangular boron nitride that we placed on top. And the fourth and final step is to transfer the crystal onto a clean substrate. And that is what the crystal looks like. So to summarize, these are the 3 flakes that I started with. We have our top and bottom layer of boron nitride and then our monolayer of graphene. This is what the crystal structure looks like after the assembly process and its corresponding high contrast optical image. So now that we have the crystal, we use Raman spectroscopy, which is a tool that we use to measure how the crystal lattice is vibrating, and we do this by using a laser. We shoot the laser light at the crystal. The crystal reflects light back out, which is picked up by the spectrometer. The data from the spectrometer allows us to calculate how much energy transfer occurred during the interaction between the laser and the crystal. And this shift in energy gives us information about the vibrational modes of the crystal, which we call Raman modes. Graphene has 2 characteristic Raman modes. The first is the G mode that has an energy shift around 1580 inverse centimeters. And the 2D mode, which we are primarily interested in, has an energy shift around 2700 inverse centimeters. These are plotted using a continuous distribution function, and the widths of these peaks tells us a lot about the thickness of graphene. To show you what this looks like, I have an optical image of graphene. So here you can see a single layer, which is basically translucent, a bilayer, and then a multi-layer. And then we can map out this region to see what those varying thicknesses are. So in purple, that directly corresponds to this single layer of graphene, and it is about 20 to 30 inverse centimeters. All of this area in orange is bilayer graphene, which is about 60 inverse centimeters. So if you look back at the peaks of these 2D Raman modes, you can see that the monolayer of graphene has a smaller peak when compared to the bilayer graphene. And we can perform this same concept to twisted bilayer graphene. So here is the image of the crystal that we created. And then if we do a small mapping of what this looks like, you can see that it's very homogeneous and the width is all in the 40 to 50 inverse centimeter range, which is in between the values for monolayer and bilayer graphene. We measure the total induced strain from the spread of the 2D and G frequencies. Crystal strain with random orientation is about 1%, and our analysis shows that the strain induced by the fabrication process is about 0.05%, which is extremely low. To conclude, the techniques that I'm using show promising results. So for future work, I will continue to create more of these crystal heterostructures and ingest the techniques if needed, and to study the properties of the superconducting state of twisted bilayer graphene. Thank you.